let's move on to our second scheme. So our second scheme, if we go back to the earlier slide, we said that we can either store pointers in the instruction queue and have pointers in the reorder buffer, or we can just store the values. And if you go read the original reservation station paper by Tomasulo, he actually stores the values in the reservation station, or we're calling instruction queue, and the reorder buffer. OK, so a couple things change when you do this. One structure is missing. First of all, there is no physical register file. We removed that. We're going to store in-flight instructions in a merged reorder buffer physical register file effectively. Second thing that's changed here is we no longer have a free list. And we'll see in a minute why we don't need the free list. But instead, we're basically just going to use different reorder buffer entries to keep track of our free list. And we're going to have to modify a bunch of stuff here. We're going to actually keep values in our reorder buffer instead of a pointer. Our renaming table is going to be modified. Our instruction queue is now going to be able to keep track of actual data values. And our physical register file, as I said before, has gotten merged into our reorder buffer. For completeness here, let's take a look at the where things get read and written in the pipeline. And one notable change I wanted to say here is the architectural register file, which in previous architectures was only written. We didn't do reading of it except on rollback. We now actually read from it because we might need to go find some canonical state there in this architecture. So we add an R there to denote that. OK, so let's look at how we have to modify the reorder buffer. Still looks like our reorder buffer from before. We need to know, for the same reason in the pointer-based design, we still need to know the architectural register number for the particular instruction. So this is when we go to write to the architectural register file, where do we write to it? Because we did renaming, so we have more physical registers. We can't just have an identity map there anymore. And now, we got rid of a lot of that other complexity we had, but we added a bunch more bits to go do this. We now actually can store values in our reorder buffer. So what this is instead of values waiting in the physical register file to be committed, they're just going to stick around in the reorder buffer entry, which is interesting. And so it's going to stick around in here while it's waiting, while it's pending, and then it's actually going to write to the architectural register file when it gets committed. OK, so we also modify the instruction queue. So this is going to tell us where to go get the values when we're going to go execute. It's also going to store the values now. So what's interesting about this is if you go back and look at the Tomasulo algorithm paper, they broadcast commits that are happening. And those commits end up in the reservation station of the actual value. So we're actually going to store in these two source operands here the values if we get a instruction which commits. If the instruction is pending, if it's in flight, we can't go and just get the value, because the value doesn't exist. It's being calculated. And we have this dependent instruction sitting here waiting for something. So instead, if it's pending, our source field, we're not going to store the value in here, but we're going to store a identifier into the reorder buffer. And that what it's going to do is it's going to name the exact instruction that has to complete in order for this value to be ready to execute. So if you think about this from sort of the Thomas-Wheeler's algorithm perspective, there's these sort of broadcasts coming back. And what this is going to allow us to do is say, oh, there's a broadcast reorder buffer entry 7 just committed. Or actually, we probably don't even need that. We probably just need it to stop being pending. We just need to get it to be finished, because then it'll be deposited in the reorder buffer. We can go pick that value out at that point and store it here. And then we can basically have the other instructions that are renaming and executing, which go and blow away that value. But because we stored the value here, we have the most up-to-date value for that register. And we know it's no longer pending, and it's valid, and it's ready to go, at least this one. And we might have to wait for both of these to get ready in order for an instruction to leave the instruction queue. OK, so the rename table also changes a little bit, not as much as the other one, the other structures. It's still indexed by the register. We're looking for register 2, we'll say. It'll tell us where to go look for that. There's a couple different places where it's going to tell us to go look for it. It's going to tell us either it's in flight, and it's going to put the identifier into the reorder buffer. So it's going to say when that value gets into the reorder buffer and the instruction transitions to finish, but maybe not yet committed, it's going to tell us where to go get it. And that's important for subsequent instructions. They're going to read the rename table to go find the value. Or it's possible that the most up-to-date value is actually in the architectural register file, and we need to go look there. So let's say the reorder buffer, you haven't written, let's say, to register 2 in a very long time. And lots of other instructions execute. And the reorder buffer gets filled up with other things for other instructions for different destination registers. It's very possible that the canonical place to go look for the value is in the architectural register file. And we need to track that. So we sort of have 2 bits here that sort of just say where to go look for it. Either it's in the architectural register file, or whether it's in flight. And then if it's in flight, we have to go look down here. And if it's in flight, that means that if p is, let's say, 1, it's actually in flight. And if it's 0, well, it's sitting in the reorder buffer waiting to retire. This is just going to tell us where to go find the actual value for subsequent instructions that want to go read the rename table to go find the value. OK, well, we'll move on. And we'll look at the eye chart here again. And what's interesting about this is we no longer have a free list. We got rid of that structure, so we don't have to worry. Our renaming table, instead of having actual physical registers, it's going to have reorder buffer entries. We'll call that a physical register. We've basically merged our physical registers and our reorder buffer together. And similar sorts of analogs happen to when something becomes free, but it looks a little bit different. So when something becomes free, we're going to actually change the valid bit in the rename table to a 0. And that's effectively the same thing as becoming free. And there's analogs there between these 2 designs. They're almost exactly the same from that perspective, from a logical perspective. But when you become free, you basically can remove it from the table. So how do we do the mapping from the architectural register to physical register? Yeah, it could be random. In this design, it's a little bit different because you're basically going to be pulling out of the reorder buffer in order to some extent. You're going to, your physical register number is going to be your reorder buffer entry slot number. And because we want to retire in order, we're basically going to allocate from that in order. So it's not really random. It's just sort of the next reorder buffer entry. let's see. Any other points I want to make here? Actually, OK, I want to make a point. It's around, OK, so I think what I said was a little bit confusing. So I want to clarify this. When do you deallocate a reorder buffer entry? Because it's a little bit different than deallocating a physical register entry. You apply the same algorithm we applied before. When you go to actually commit the instruction to the architectural register file, that's when it's becoming free. It's basically stopping being used here. That's a little bit different than the, there's analogs to before, but we're effectively moving it out of the reorder buffer into the architectural register file, and at that point it becomes free. So I want to actually strike what I just said before about it's exactly the same. It's different, but subtly, that when you go to actually commit the instruction, you're moving it to the architectural register file, and you effectively deallocated that reorder buffer entry, and you've updated the rename table. So that's subtle. That's actually subtle there. So we're actually, when it commits, it stops being used, which is different than a later instruction actually writing that. So that is quite a bit different. Sorry about that.